In the silent reaches of the cosmos, a star begins to die. It does not fade gently into darkness, nor surrender quietly to time. Instead, its death is a violent implosion, a collapse so absolute that the fabric of nature itself seems to recoil. A sun, once wide enough to cradle entire solar systems in its light, is crushed into a sphere no larger than a city. Its radiant body contracts, folding in upon itself, until matter is compressed to the limits of physical possibility. What remains is not a familiar star, but a core of impossible density, a compact star. Here, the weight of millions of Earths rests in a single object. A teaspoon of its substance outweighs a mountain, defying every measure of scale the human mind can grasp. The familiar world of atoms and electrons disintegrates under its gravity, leaving behind something that is neither fully matter nor fully energy, but a state of being beyond the reach of laboratories or equations. To stand against such a presence is to stand at the edge of comprehension. How can something so small in size wield such crushing force? How can a collapsed sun dictate the flow of time, bend the path of light, and twist the very geometry of space? These are not corpses of stars, but engines of mystery, cosmic hearts beating with the weight of collapsed universes. And so, a haunting question lingers in the dark. When the universe bends beneath the crushing force of a dying star, what is it revealing to us, an end or a beginning? Long before equations and telescopes, the ancients looked upward and wondered why the stars shone at all. To them, the death of a star was not a physical process, but a cosmic myth. They saw divine fires extinguished, gods torn apart in the heavens, or eternal torches carried into the underworld. Stellar death became prophecy, woven into stories of endings and rebirths. What they could not know was that these myths, poetic and eternal, would one day find echoes in the reality of physics, that the collapse of a star is indeed a kind of rebirth, one more violent and mysterious than their imagination ever dared. It was not until the 19th century that science began to pierce the veil of starlight. Through the new art of spectroscopy, astronomers unraveled the light of distant suns and found a startling truth. Stars were not ethereal lanterns, but made of the same elements as Earth, hydrogen and helium. Carbon and oxygen, the building blocks of the familiar, were also the bricks of the distant. This revelation grounded the heavens into the same reality as the soil beneath human feet. Yet with this insight came a deeper question. What force allowed such immense furnaces to burn, and what fate awaited them when their fuel was gone? The puzzle consumed minds. Stars burn for millions, even billions, of years, but nothing lasts forever. The energy of fusion could not be infinite. Some predicted that stars, stripped of their fire, might collapse inward, crushed by their own gravity. But how far could such a collapse proceed? Would matter simply compress into a smaller star, or was there a final wall beyond which physics itself would break? In the 1930s, a young physicist named Subramanian Chandrasekhar carried these questions with him across oceans. As a student traveling from India to England, he calculated the fate of white dwarfs, those faint stellar remnants left behind after a star sheds its outer layers. His mathematics revealed a limit, a boundary beyond which gravity could not be resisted. If a star were too massive, it would not stop at the gentle cooling of a white dwarf. Instead, it would collapse into something denser, stranger, and more extreme. This threshold became known as the Chandrasekhar limit, but such ideas unsettled the scientific world. Many dismissed them as abstractions, mathematical curiosities with no place in nature. Even Albert Einstein doubted that stars could collapse into objects so dense that not even light could escape. To leading minds, the notion seemed absurd, a violation of common sense. The universe, they argued, must surely possess hidden laws that prevented such monstrosities, yet history would prove otherwise. Slowly, evidence began to mount that nature did not flinch from extremes. The seeds of the idea had been planted that when the fire of a star dies, the cosmos leaves behind not silence, but cores of unimaginable density, compact stars that would one day be recognized as neutron stars and black holes, objects that, in their crushing force, twist not only matter, but the very structure of reality itself. The roots of understanding, stellar death, reach back to the very beginnings of astrophysics. In the early 20th century, the question of why stars shine dominated scientific thought. Theories abounded, but most fell short. Gravitational contraction was one candidate, the slow collapse of a star releasing energy over millions of years. Yet this explanation faltered when calculations showed that it could only power stars for tens of millions of years at most. The Earth itself, by geological evidence, was already billions of years old. There had to be a deeper, hidden engine at work. This realization laid the groundwork for the discovery of nuclear fusion, the process by which hydrogen atoms merge into helium, releasing energy that sustains stars across cosmic epochs. Once the source of stellar power was revealed, the next question was inescapable. If fusion held stars against gravity, what happened when the fuel was gone? It was clear that equilibrium could not last forever. Gravity is patient, inexorable, and relentless. Left unchecked, it pulls everything inward. For small stars like the Sun, scientists realized, the end would be modest. A shedding of outer layers, leaving behind a white dwarf, a dense but stable ember that glows faintly as it cools. But what of larger stars, the titans many times the Sun's mass? Would they simply collapse into larger white dwarfs, or was there another, darker destiny awaiting them? It was here that Chandrasekhar's calculations struck like lightning against the complacency of established thought. During his voyage to England in 1930, he worked relentlessly, scribbling equations that seemed to pierce into the hidden laws of stellar death. His conclusion was shocking. No white dwarf could exist beyond about 1.4 times the mass of the Sun. Anything heavier would succumb to gravity's crushing force. Such a star, he argued, would collapse further into an unknown state of matter. To many in the audience of the Royal Astronomical Society, his conclusion was unthinkable. Arthur Eddington, one of the era's most respected astronomers, publicly ridiculed the idea, suggesting that nature had ways of preventing such absurd outcomes. The clash was not just about physics, it was about imagination. Could reality itself be stranger than the limits of human intuition? The resistance to Chandrasekhar's limit reveals a deeper theme in the history of science. Humanity's hesitation to accept the cosmos as it is, rather than as it should be. The very notion of matter compressed to such extremes felt alien, even offensive, to minds shaped by classical physics. Yet the equations of relativity and quantum mechanics, then still fresh in the scientific world, pointed toward possibilities that defied comfort. Einstein himself was wary of singularities, proposing mechanisms by which collapsing stars might stabilize before reaching infinity. Others argued that dense matter would exert unknown pressures that stopped the collapse. Still, the mathematics left little room for escape. A truth was beginning to unfold, that the universe did not shy away from the grotesque, but embraced it. Beyond the theoretical battles, evidence was accumulating from the skies. Observations of novae and supernova, sudden stellar outbursts, hinted that stars ended their lives in violent transformations. These explosions expelled matter into interstellar space, enriching galaxies with the elements that would become planets, oceans, and life itself. Yet something always seemed to remain at the core. The fading light suggested not annihilation, but survival in another form. Slowly, the concept of compact remnants, objects left behind by stellar death, began to take root by the late 1930s and 1940s. Theorists like J. Robert Oppenheimer and George Volkoff began to extend Chandrasekhar's work. They considered the extreme case. What if protons and electrons were forced together under immense pressure, fusing into neutrons? This vision gave birth to the idea of neutron stars, celestial bodies composed almost entirely of neutron matter. The calculations suggested that such stars would be no larger than a city, yet hold masses greater than the sun. Their densities were beyond anything the human mind could comfortably imagine. The very atoms that defined matter would cease to exist. Nuclei would be crushed into a sea of neutrons. Space and time themselves would strain under their weight at the time. These ideas remained speculative, theoretical structures built on equations rather than direct evidence. Yet they marked the birth of a new cosmic archetype, stars that did not simply die, but transformed into entities so extreme they bordered on the incomprehensible. Humanity was standing at the threshold of recognizing a new class of objects hidden in the shadows of stellar death. What began as myth had become mathematics, and mathematics was preparing to reveal truths that myth had only dimly sensed. That endings in the cosmos are not simple extinguishings, but gateways into deeper mysteries. The idea that a star could collapse without limit was one of the most unsettling predictions, to emerge from the marriage of relativity and quantum theory. Even Albert Einstein himself struggled with it. In 1939, alongside his collaborator Nathan Rosen, he proposed that such collapse might be avoided by an internal pressure or exotic mechanism, sketching the concept of a bridge of space and time, what later generations would call a wormhole. His motivation was not only mathematical curiosity, but also discomfort. Einstein believed nature abhorred infinities, and the notion of a singular star, an object collapsing to a point of infinite density, seemed to him less like physics and more like a flaw in the equations. He sought to close the door before others could walk through it. Across the astronomical community, the mood was similar. Many regarded predictions of singularities as mathematical mirages born from pushing equations beyond their valid domain. Stars, they argued, were real and observable, while infinities belonged to philosophy. White dwarfs, at least, had been detected. Their tiny size and faint glow were strange but measurable. They fit within the boundaries of imagination, a step beyond the familiar but not outside it. Neutron stars, by contrast, seemed like fantasy, dense to the point that matter itself would be stripped of its identity. Atoms crushed until nothing recognizable remained. And black holes, if one dared even speak the name, were dismissed outright as absurdities, the stuff of speculative nightmares rather than scientific realities. The challenge was not only mathematical but psychological. To picture matter compressed beyond atomic structure required abandoning the very building blocks of the known world. Electrons, protons, the stable scaffolding of atoms, all would dissolve under pressure into forms of matter no human had ever encountered. Could nature really permit such transformations? Or was there a hidden law, yet undiscovered, that would rise up at the last moment to halt collapse, preserving the cosmos from such monstrosities? The tension was as much philosophical as it was scientific. The question cut at the boundary between human intuition and the cold indifference of the universe. Yet the momentum of history was shifting. In the shadow of a world tilting toward war, physics itself was entering a new age. The discovery of nuclear fission in the late 1930s revealed that unimaginable energies lay locked inside the atom, waiting to be unleashed. The collapse of a star was no longer an abstraction. The world was learning that matter itself held terrifying depths. The rise of nuclear research, driven by military necessity, forced scientists to confront realities that mirrored the very processes unfolding in distant stellar cores. Even as telescopes fell silent in wartime, laboratories roared with experiments that deepened humanity's grasp of dense matter, preparing minds to understand what once seemed unthinkable. In these years of uncertainty, the divide became clear. White dwarfs were accepted, their existence confirmed by light and spectra. Neutron stars lingered in the margins, a bold hypothesis few were willing to champion. And black holes remained exiled to the realm of impossible ideas, mathematical artifacts to be discarded. The universe, however, would not wait for human consensus. It held its secrets in silence, while minds argued over whether they could even exist. Debate reached a turning point in 1939, when J. Robert Oppenheimer and his student Hartland Snyder dared to follow mathematics further than anyone else. Their calculations, derived from Einstein's own equations of general relativity, suggested that once a massive star exhausted its fuel and pressure could no longer resist gravity. No known force could halt the collapse. The result was not a stable star, nor even a dense core like a white dwarf, but a runaway implosion. Space itself would curve inward, light would be trapped, and the star would vanish from view behind an invisible boundary. Oppenheimer and Snyder described this outcome in austere terms, but the implications were staggering. The cosmos might contain objects that erase themselves from sight, leaving only gravity as their lingering presence. Yet their work arrived at a time when the world was bracing for global conflict. The paper was noted, but soon forgotten, buried beneath the urgency of war and the unease of a concept that seemed too extreme to be real. For many, the resistance was not born only of science, but of imagination. Astronomers had always dealt with what could be seen, weighed, and measured. The notion of an object so dense that its surface was forever hidden, its light unable to escape, violated the very premise of observational astronomy. How could something invisible ever be proven to exist? The discipline, rooted in centuries of patient observation, recoiled at an idea that replaced sight with absence. To some, it felt less like discovery and more like surrender, an acknowledgement that the universe contained places beyond the reach of even the most powerful telescope. Such a notion cut against the confidence of a scientific era, convinced that reason and measurement could eventually pierce every veil. There was also the unsettling symmetry between the cosmic and the human. As theorists speculated about matter compressed into forms unrecognizable, the laboratories of Earth were splitting atoms and releasing energies capable of reshaping civilization. The fire that drove stars had been summoned into bombs. With Hiroshima and Nagasaki, the world learned that the structure of matter could be undone, that energies locked in the nucleus were not distant mysteries, but forces that could alter history. In this context, the idea of stellar collapse no longer seemed entirely detached. The same physics that governed the hearts of stars was now manifest in laboratories and on battlefields. Gravity and nuclear force, once abstractions of distant astronomy, had revealed themselves as powers that could both illuminate the cosmos and plunge humanity into shadow. When the war ended, astrophysics returned to its long-ignored puzzles. but with minds tempered by the recognition that nature was more violent, more extreme than once imagined. The skepticism lingered. Black holes were still regarded as improbable, neutron stars as doubtful, but the seeds had been planted. The great reluctance to accept collapse was no longer absolute. Experiments in particle physics had shown that matter could transform under pressures and energies no one had believed possible. And if such transformations could be coaxed in earthly accelerators, how much more might occur in the furnace of a dying star, where mass greater than the sun was being crushed into the volume of a city. The divide, however, remained sharp. For decades after Oppenheimer and Snyder, the majority of astronomers treated compact stars as a fringe curiosity. White dwarfs were real, stable, and understood. Neutron stars were whispers, possible but unproven. Black holes, though anchored in mathematics, were still regarded as ghosts, theoretical abysses without observational evidence. The universe had unveiled the possibility of monsters, but the scientific world was not yet ready to believe in them, and so the questions lingered in the shadows of theory, awaiting the instruments, the data, and the courage to look again at what the equations had long been trying to say. In the late 1960s, a whisper from the stars began to pierce the static of Earth's radioscopes. It arrived as a rhythm, a steady pulse that beat with a precision no natural source was expected to produce. At first, it was dismissed as interference, some echo of terrestrial machines. But the signal persisted, unwavering and unearthly. It was Jocelyn Bell, a graduate student scanning miles of paper chart recordings, who noticed the pattern, a pulse arriving every 1.3 seconds, as if the universe itself were ticking with a hidden clock. The discovery was so precise, so mechanical in nature, that for a fleeting moment the team half-jokingly labeled it LGM-1 for Little Green Men, yet what they had uncovered was far stranger than any alien beacon. It was the heartbeat of a collapsed star, the first neutron star ever glimpsed by humanity. The revelation shattered decades of hesitation. The compact stars that had lingered in theory since Chandrasekhar, since Oppenheimer, were no longer mathematical curiosities. They existed, spinning in the void with magnetic fields 1,000,000,000,000 times stronger than Earth's, broadcasting their existence across light years with beams of radio energy. The object Bell had detected was no larger than a city, yet it spun with the weight of a sun. Its mass crushed into a core so dense that matter itself was unrecognizable. The very atoms had collapsed, electrons forced into protons to form neutrons. A solid sea of nuclear matter pressed to unimaginable density. For the scientific community, the impact was profound. Theoretical speculations had become empirical truth. The cosmos was not merely populated by luminous stars and swirling galaxies, but by hidden relics of collapse, stars that had died, yet continued to announce their presence with mechanical certainty. Pulsars became cosmic lighthouses, each one sweeping its beam across the galaxy, reminders that even in death, stars could carve patterns of order into the chaos of space. These signals did more than confirm theory. They provided astronomers with a tool to probe the structure of matter itself, the way a pulsar spins, the way it slows over time. The precision of its pulses all revealed clues about what lay beneath the star's crust, about the nature of matter under pressures no laboratory could hope to recreate. Yet the instruments of the era were blunt compared to the mystery they had unveiled. Radio telescopes strained to catch the faint pulses, their sensitivity limited, their resolution blurred. Each detection was a glimpse through fog, enough to confirm existence, but not yet enough to reveal detail. Still, each new pulsar mapped was another piece of evidence, another declaration that the universe contained objects beyond imagination. The skepticism that had silenced earlier theorists gave way to astonishment, even awe. Stars could die and yet endure, not as corpses drifting in silence, but as spinning clocks, their precision rivaling that of atomic timekeepers on Earth. In these discoveries, there was also an undercurrent of something deeply human, a shock that nature had not only allowed such collapse, but had woven it into the fabric of reality. If neutron stars could exist, then perhaps black holes too were waiting to be confirmed. Perhaps the universe harbored realms where the known laws broke down entirely. Pulsars were not just a discovery of astrophysics. They were a door creaking open, revealing that the cosmos was stranger, harsher, and more intricate than anyone had dared to believe. And with every pulse, every heartbeat of a dead star, came the reminder that collapse was not annihilation, but transformation, a rebirth into something both terrifying and profound. The discovery of pulsars did not remain an isolated marvel. Soon, other radio observatories began to report similar signals, each one a lighthouse blinking across the night. What had once seemed impossible, the very notion of a collapsed core persisting after the death of a star, was now undeniable. The cosmos was suddenly populated with these strange metronomes, each one spinning with dizzying speed, some rotating hundreds of times per second. Their sheer precision was unlike anything in nature, pulses arriving so regularly that they rivaled the atomic clocks engineered by human hands. Astronomers began to realize they were not simply observing curiosities of stellar death, but perfect laboratories carved by the universe itself. These stars offered a chance to peer into conditions no experiment on Earth could replicate, to touch the threshold of nuclear matter under pressures trillions of times greater than those within an atomic nucleus. As the catalogue of pulsars grew, so too did the weight of their implications. Here were stars compressed to the scale of cities, yet so stable that they could spin ceaselessly for millions of years. Their magnetic fields arced through space with ferocity, funneling charged particles and sculpting winds that extended far beyond the star itself. To study them was to glimpse the architecture of matter stripped to its bare essence. The very crust of a neutron star was imagined as a lattice of nuclei, while deeper within lay seas of neutrons flowing like a quantum fluid. At still greater depths, theorists wondered if quarks, the constituents of protons and neutrons themselves, might dissolve into a new state of matter, a quark soup where familiar particles could no longer exist. With each new observation, questions multiplied, and with them a humbling recognition. These compact stars were more than remnants. They were natural experiments, conducting physics at scales unattainable in any earthly chamber. And yet, for all their precision, pulsars also embodied a profound mystery. Why did they spin so fast? And how could they maintain such perfect rhythm across spans of cosmic time? Each rotation bled energy into the surrounding space, and yet the stars persisted, slowing so imperceptibly that only decades of observation revealed the change. To listen to a pulsar was to listen to a clock wound by forces beyond human comprehension, a timepiece forged in the crucible of collapse. It was as if the dying star, rather than falling silent, chose to leave behind a cosmic signature, a pulse, a heartbeat echoing across light years. As though refusing to be forgotten, the impact on human imagination was profound. In the public eye, pulsars carried an aura of mystery, often invoked as signals from extraterrestrial civilizations or as celestial beacons guiding explorers across the stars. But beneath the poetry of speculation lay a deeper truth. The universe itself had provided instruments of astonishing precision, embedded in the wreckage of its own violence. These were not relics of destruction, but tools of creation, cosmic laboratories revealing truths about gravity, matter, and time. Each new detection expanded the map of what was possible, whispering that beyond neutron stars lay realms even stranger, waiting to be uncovered. The sky had always been studied in light visible to the eye. But in the middle of the 20th century, a new frontier opened, the sky as seen in X-rays, where optical telescopes revealed a universe of gentle starlight and swirling galaxies. X-ray astronomy unveiled something altogether harsher, a cosmos where violence blazed unseen by human vision. Satellites lifted detectors above the filtering veil of Earth's atmosphere and immediately found skies alive with strange flares and flickers. These were not the familiar thermonuclear fires of main-sequence stars, but eruptions of energy so intense that only compact stars could be their source. Suddenly, neutron stars, once abstract curiosities, became luminous predators revealed in high-energy light. Some of the most startling discoveries came from binary systems, where a compact star orbited a more ordinary companion. Gravity, merciless and insatiable, drew streams of matter from the living star onto the collapsed one. Gas spiraled inward, forming accretion disks that blazed with temperatures hotter than the sun, releasing torrents of X-rays detectable across light years. These were stellar vampires, feeding on their neighbors, transforming the quiet balance of starlight into a stage for violent flares. What theory had only sketched in equations was now blazing on screens in mission control rooms. Compact stars were no longer hypothetical. They were radiant in their hunger, devouring matter and releasing energies, rivaling entire galaxies in miniature bursts. And yet, among these collapsed cores, some were even stranger. The discovery of magnetars revealed a class of neutron stars so extreme that their magnetic fields defied comprehension, while Earth's magnetic field gently guides compasses. A magnetar's field was trillions of times stronger, capable of distorting atomic structures, tearing molecules apart, and unleashing bursts of gamma radiation powerful enough to momentarily outshine the Milky Way. In 1979, one such flare swept through the solar system, saturating detectors and startling astronomers with its sudden brilliance. In the decades that followed, magnetars would prove themselves the most terrifying engines in the galaxy, their very existence a challenge to human imagination. These were not simply remnants of collapse, but crucibles where the laws of physics strained under pressures beyond laboratory reach. Even in their regularity, compact stars revealed new marvels. Pulsars, timed with careful precision, proved to be more accurate than the atomic clocks constructed on Earth. Their signals, echoing across space with unwavering rhythm, could be used to navigate the galaxy, like celestial GPS beacons offered freely by the universe. Each rotation carried the weight of stellar collapse, yet also the gift of order in chaos ticking, patient, unyielding across the abyss of time. Astronomers began to map not only their positions, but their slow decays in speed, measuring how their energy seeped away into gravitational waves and radiation. In doing so, pulsars became both clocks and laboratories, each one a silent testament to the endurance of collapsed matter. Perhaps the most profound breakthrough came with the discovery of binary systems where two neutron stars orbited one another in a cosmic dance. Their movements traced the curves of spacetime itself, providing natural experiments for Einstein's general relativity. In 1974, Russell Hulse and Joseph Taylor detected such a pair and carefully measured the subtle changes in their orbits. Over years, the stars were observed to spiral inward, losing energy not through light, but through ripples in spacetime, gravitational waves. It was the first indirect evidence that Einstein's prediction was true. Decades before LIGO's detectors would hear the faint tremor of colliding black holes, neutron stars had already whispered the existence of these waves too. Anyone who could measure carefully enough, with each observation, the perception of compact stars shifted. They were no longer rare oddities hiding in dusty corners of theory, but integral actors in the life cycle of the cosmos. Every massive star that lived and died could end as one of these dense remnants, littering the galaxy with pulsars, X-ray binaries, and magnetars. They were not occasional curiosities, but a fundamental consequence of stellar death. And with this realization came a deeper awareness. The universe is not merely sustained by birth and radiance, but by collapse, by transformation into states of matter and energy more alien than imagination once allowed. The stars that had once seemed eternal revealed themselves to be impermanent, collapsing into cores that twisted not only space and time, but the human sense of what was possible. By the close of the 20th century, the pursuit of compact stars had become a global endeavor, driven by instruments lofted into orbit with singular purpose. The Chandra X-ray Observatory, launched in 1999, delivered clarity that ground-based telescopes could never achieve, with mirrors polished to perfection and detectors sharpened to catch the faintest glimmers of high-energy light. Chandra revealed neutron stars in exquisite detail. It showed their surfaces scarred by hotspots, their accretion disks torn and twisted by gravity, their surroundings seared by particle winds accelerating to near light speeds, where once neutron stars had been inferred by their pulses alone. Now their violent environments were painted vividly in exposing a realm of energy that dwarfed the familiar glow of ordinary stars. These new eyes upon the sky also captured the restless lives of magnetars. Long after their initial discovery, their tempers continued to astound. Bursts of gamma radiation erupted without warning, sometimes so powerful that they briefly blinded satellites designed to watch the entire universe. One flare, recorded in 2004 from the magnetar SGR 1806-20, unleashed more energy in a fraction of a second than the sun would emit in 100,000 years. Its shockwave rippled through the solar system, compressing Earth's magnetic field and jamming spacecraft instruments. Such events confirmed that magnetars were not dormant relics, but active, volatile presences, stellar cores so tightly wound with magnetic energy that they seemed more akin to coiled springs of the cosmos than to quiet remnants of collapse beyond their violence. Neutron stars also became tools for testing the deepest laws of physics. The precision of pulsar timing allowed astronomers to study gravitational interactions with accuracy impossible in laboratories. In binary pulsar systems, the minute drift of orbital periods testified to energy lost through gravitational radiation, a phenomenon that confirmed Einstein's predictions with remarkable fidelity. Observing such systems was like reading a cosmic manuscript, each line of data inscribed by the curvature of spacetime itself. When pulsars orbited within regions of intense gravity, they revealed how time slowed, how space bent, and how the universe obeyed rules that were elegant yet merciless. These measurements did more than verify relativity. They showed how neutron stars were themselves instruments, natural detectors sculpted by collapse to measure the architecture of the cosmos. Perhaps most transformative was the realization that these objects were not cosmic rarities but common outcomes of stellar death. Every massive star that burned and exhausted its fuel faced one of two fates: to collapse into a neutron star or to vanish more completely into a black hole. The galaxy, once imagined as a collection of radiant suns, was now understood as a graveyard littered with collapsed cores, each one a silent survivor of a supernova's violence. With modern surveys, hundreds of pulsars were catalogued, and their distribution mapped across the Milky Way revealed that compact stars were not scattered anomalies, but threads woven into the structure of the galaxy itself. Their presence redefined the balance of matter, contributing to the unseen mass that helps shape the motion of stars on galactic scales. The deeper astronomers gazed into this domain, the more the boundary between knowledge and mystery blurred. Were the interiors of neutron stars truly seas of neutrons, or did stranger states of matter emerge, quark, matter, hyperons, or even phases of exotic particles, unimagined in earthly accelerators? The light impulses that reached Earth could not yet reveal the answer, but they offered tantalizing hints. Slight irregularities in timing, sudden glitches in pulsar spin, and the unpredictable tempers of magnetars suggested that beneath their crusts something dynamic and alien stirred. Compact stars were no longer just confirmations of stellar collapse. They had become laboratories of the unknown, where the laws of physics, tested to their limits, hinted at new realms awaiting discovery. The breakthroughs of the late 20th century left the scientific community standing at a precipice. Neutron stars had moved from theory to observation, from rare anomalies to central figures in cosmic evolution. Their X-ray flares and magnetic storms illuminated the violent mechanics of stellar death. Their precise timing measured the curvature of spacetime with unmatched accuracy. Their ubiquity reshaped the very picture of the galaxy. Yet for all the clarity gained, their cause remained cloaked in secrecy. To peer deeper into their nature would require instruments beyond the reach of the present, and patience measured not in years, but in generations. The universe had unveiled its lighthouses and its storms, its clocks and its crucibles, but it still held back its final secrets. The next steps would carry astronomers further into a domain where science itself began to brush against the edge of the unknowable. They stand at the edge of comprehension, compact stars, the remnants of collapsed suns. Though their existence is no longer in doubt, their nature remains shrouded in mystery. Each one is a laboratory of matter forged under conditions that Earth could never recreate. No particle accelerator, no magnetic confinement chamber, no terrestrial experiment can reach the densities and pressures that dwell within their cores. In these stellar crucibles, the familiar scaffolding of atoms is stripped away, and the universe reveals states of matter that challenge imagination itself. At first glance, neutron stars appear to be paradoxes of stability. How can something so small resist the collapse that destroys stars many times their size? Their survival is owed to the collective resistance of neutrons, particles squeezed shoulder to shoulder in densities that defy comprehension. Yet this stability has its limits. Push just a little harder, pack a little more mass, and the star crosses a threshold beyond which even neutrons cannot endure. At that boundary, it does not remain a star at all, but sinks into the abyss of a black hole. Why some collapsing stars halt as neutron stars, while others fall deeper into the void, is one of astrophysics' great puzzles. It is a question not only of mass, but of the unknown physics that governs matter, when it is pressed past every frontier known to science. Theorists have long speculated about the hidden interiors of these objects. In the outer layers, where densities are lower, the material may resemble an ocean of neutrons flowing beneath a crust of exotic nuclei. Deeper down, where pressures rise beyond the nuclear scale, the neutrons themselves may dissolve into their constituent quarks, producing a soup of fundamental particles more akin to the primordial universe than to anything found today. Some models propose the existence of hyperons particles containing strange quarks arising in the star's heart, where the forces of nature are twisted into unfamiliar forms. If such states exist, they would be unlike anything humanity has ever touched, matter not solid, liquid, or gas, but an entirely new phase dictated by gravity's relentless hand. This enigma grows sharper with the question of mass. The Tolman-Oppenheimer-Volkoff limit, first calculated in the 1930s, sets the theoretical ceiling for a neutron star's weight. Cross this limit, and collapse into a black hole becomes unavoidable, yet the precise value of this limit remains uncertain. Observations of massive neutron stars, some weighing more than 2 suns, push theorists to revise their calculations, suggesting that the physics of ultra-dense matter may allow greater resilience than once believed. Each new discovery redraws the fragile boundary between star and singularity, a line that defines not only the fate of collapsed suns, but the laws of matter itself. Adding to the puzzle is the astonishing speed at which some neutron stars rotate. Millisecond pulsars whirl hundreds of times each second, their surfaces racing at a significant fraction of the speed of light. Such rapid spin should tear a star apart, and yet they endure, held together by gravity's iron grip. How such dizzying rotation is achieved is itself a story of cosmic cannibalism. Many are thought to have been spun up by siphoning matter from companion stars, each drop of stolen mass adding momentum until the neutron star becomes a spinning dynamo of unimaginable precision. Their pulses arriving on Earth with timing more accurate than atomic clocks suggest that beneath the surface of these furious engines lies a stability that is as enigmatic as it is unyielding. Every new observation deepens suspicion that compact stars conceal realms of physics unseen elsewhere. They embody contradictions, immense yet tiny, fragile yet indestructible, simple in appearance yet endlessly complex within. They are reminders that the universe does not yield its secrets easily. The more clearly astronomers gaze upon them, the more their interiors seem to vanish into uncertainty, as though wrapped in a veil that no telescope can pierce. To unlock their mysteries will require not only sharper instruments, but new ideas, new theories, and perhaps an expansion of physics itself. For in these stellar remnants lies a truth larger than any star, that even after centuries of inquiry, the cosmos still keeps secrets vast enough to humble the human mind. And in the silent hearts of neutron stars, the universe may be storing answers that will redefine not only the fate of dying suns, but the very nature of reality. Inside these enigmatic spheres, nature conducts experiments on a scale no laboratory could dream of. The neutrons that resist collapse are not frozen in place. They form a quantum fluid, flowing without viscosity in a state known as superfluidity. This bizarre property allows them to slip past one another without friction, giving rise to phenomena unseen elsewhere in the universe. On the outer crust, another layer behaves like a rigid lattice of nuclei, locked together with almost crystalline order. Between these extremes, the rigid and the fluid, lies a frontier of physics where matter's behavior cannot be described with certainty. This is the realm where pulsar glitches are born, sudden, unpredictable jumps in rotation that ripple through the cosmos. Astronomers believe these are caused by the cracking of a neutron star's crust or the sudden transfer of angular momentum from the superfluid interior. Each glitch is a message from deep within, a coded signal hinting at the star's secret architecture. To decipher those messages, astronomers have turned to instruments designed to weigh and measure with exquisite precision. NASA's NICER experiment, perched on the International Space Station, has begun to map neutron stars not by sight but by the subtle timing of their pulses. With these measurements, it is possible to estimate both mass and radius, sketching the outlines of these compact spheres against the uncertainty of theory. The results suggest that neutron stars are neither as small nor as fragile as once imagined, standing firm against collapse at sizes of about 20 kilometers across, yet with cores that could house phases of matter alien to physics textbooks. Every new observation nudges the models forward, constraining or disproving equations of state that attempt to capture the behavior of matter at densities 10 times greater than those in atomic nuclei. Yet even with these insights, the mystery grows deeper when viewed through the lens of gravity itself. In the dance of binary neutron stars, astronomers have detected ripples in spacetime, gravitational waves, faint tremors reaching Earth after journeys of billions of years. The signals, recorded by observatories like LIGO and Virgo, carry within them the fingerprint of neutron star matter. As two stars spiral inward and collide, their shapes deform under tidal forces, revealing how stiff or soft their interiors truly are. These collisions do not merely confirm Einstein's relativity. They provide a probe into the nuclear physics hidden inside stellar cores. The first such detection, in 2017, hinted that neutron star matter is unexpectedly resilient, resisting collapse longer than expected, while releasing elements like gold and platinum in cosmic alchemy. And still, uncertainty reigns. Some theories whisper of stars stranger than neutrons, hypothetical quark stars, whose interiors dissolve into a sea of free quarks, liberated from confinement by extreme density. Others suggest hybrid stars, with layers of neutrons surrounding a quark core, a structure as layered as the Earth, but operating on principles far removed from planetary geology. If such objects exist, there would be monuments to physics beyond the known, relics of conditions that resemble the universe in its first microseconds. But no telescope has yet distinguished them clearly from ordinary neutron stars. For now, they linger in the gray zone between speculation and discovery. The paradox of compact stars lies in their silence. They do not announce their secrets willingly. Their interiors remain beyond the reach of direct measurement, hidden beneath an armor of gravity that no probe could penetrate. Instead, astronomers are left with fragments of evidence. A glitch here, a pulse there, a ripple in spacetime, a flare of X. Each piece must be assembled like shards of a cosmic puzzle, and still the edges never quite meet. The more is learned, the more elusive the truth becomes, as though compact stars exist precisely to remind science that there are frontiers still untamed, landscapes where imagination must walk hand in hand with mathematics, for within these tiny, crushing spheres lies a challenge as vast as the cosmos itself. They stand not only as remnants of stellar death, but as gatekeepers of physics yet to be discovered. Each neutron star is both monument and mystery, a glowing paradox that twists the laws of matter, energy, and spacetime into unfamiliar forms. They are nature's riddles, written in the language of gravity, awaiting a generation bold enough to decipher them. They exist at the very threshold of what science dares to imagine. Stars so dense and violent that they do not simply shine, but reshape the very stage on which the universe plays out its story. Compact stars push physics to its breaking point, and nowhere is this more evident than in the cataclysm of their collisions. In August of 2017, detectors in Louisiana, Washington, and Italy captured a tremor in spacetime itself, the faint shudder of two neutron stars spiraling together after billions of years in orbit. The event, known as GW170817, was not just a confirmation of Einstein's theory, but a revelation. For as the stars merged, telescopes across the Earth and in orbit watched the sky bloom with a kilonova, a transient fireball glowing in optical, ultraviolet, and infrared light. In its fading spectrum lay the fingerprints of newly forged elements: strontium, gold, platinum. The ancient mystery of where the universe's heaviest atoms were born had found its answer, not in gentle forges, but in the crushing embrace of compact stars colliding at near light speed. Such collisions remind science that these stars are more than remnants. They are engines of cosmic alchemy, seeding galaxies with the raw material of planets, jewelry, and even human blood. And yet, the gravitational wave that heralded this discovery was unimaginably faint. Its distortion of spacetime less than the width of a proton across 4 kilometers of detector arms. That something so small could carry the story of something so vast speaks to the strangeness of this frontier. It is as though the universe whispers its secrets only to instruments tuned with the patience of centuries. But not all mysteries reveal themselves in such brilliant light. Some compact stars hide in silence, announcing their presence only through the invisible distortions they create in space and time. Magnetars, neutron stars with magnetic fields 1 trillion times stronger than Earth's twist, the very structure of light. Around them, photons split and scatter, space itself becomes polarized, and the vacuum behaves like a crystal lens. Occasionally, they roar to life with bursts of X-rays and gamma rays so intense that were one to erupt within a dozen light-years, it could scorch Earth's atmosphere. In these moments, magnetars remind science that even in apparent stillness, the universe holds reservoirs of violence beyond human comprehension. At the edge of their gravity wells, relativity becomes more than a theory. It becomes lived reality. A clock resting on the surface of a neutron star would tick more slowly than any on Earth, slowed by the sheer warping of spacetime. To orbit such an object is to skate on the razor's edge of Einstein's equations, where a small increase in velocity could send matter either crashing into the star or plunging into deeper orbits of impossible stability. Here, time itself loses its familiar flow, stretched and contracted by gravity's invisible hand, and within these environments, compact stars act as natural particle accelerators, hurling charged particles into space with energies no human machine could ever hope to achieve. Cosmic rays born in the magnetospheres of pulsars streak across galaxies, sometimes striking Earth after journeys of millions of years. They carry information about conditions so extreme that laboratories can only dream of imitating them. Each particle is a messenger, a relic of fields and forces on scales that dwarf terrestrial physics. Yet for all that has been seen, much remains hidden. Predicted phenomena, bursts of neutrinos from collapsing stars, exotic signals from quark matter, even gravitational echoes that might hint at cracks in Einstein's picture remain elusive. The silence is not emptiness, but a veil. Perhaps the signals are too faint, too rare, or too alien for current instruments to capture. Perhaps they wait for detectors not yet built, or for theories not yet conceived. The universe, it seems, guards its most profound truths carefully, offering only glimpses through events that may happen once in a century. And so compact stars remain perched on the frontier, where discovery shades into mystery, and mystery dissolves into silence. They are cosmic riddles written in fire and gravity, daring science to follow them into realms where matter, light, and time itself twist into unfamiliar shapes. In their presence, one sees both the triumph of human understanding and the infinite horizon of the unknown. The revelation of compact star collisions did more than answer ancient questions about the birth of elements. It also pushed science into an entirely new era, one where astronomy is no longer confined to light alone. For centuries, telescopes had gazed upward, interpreting the universe only through photons, faint starlight, glowing gas, distant shadows. But when neutron stars collided, the universe spoke in two voices, in the ripples of spacetime itself, and in the radiance of the kilonova. For the first time, gravitational waves and electromagnetic light were observed together, opening what scientists now call multi-messenger astronomy. It is as if the cosmos, once a silent film, suddenly gained sound. This transformation is not just technical, but philosophical. It suggests that reality is far richer than any single sense, that the story of existence cannot be captured by light alone. The significance of these cosmic collisions extends beyond the elements forged in their fire. They provide one of the few opportunities to measure the very equation of state of neutron matter, to test how matter behaves when crushed to densities billions of tons per teaspoon. The exact stiffness or softness of such matter determines whether a neutron star can resist collapse, or whether it plunges into the abyss of a black hole. Gravitational waves carry within them subtle signatures of these properties. When the stars deform as they spiral inward, their shape imprints on the wave. By reading those distortions, physicists glimpse into the unseeable, the interior of matter at densities beyond any laboratory's reach. Each signal is not just an astronomical event, but a probe into the foundations of physics itself. Yet the universe does not reveal its truths evenly. Some collisions radiate brightly, while others are shrouded in silence, hidden by dust, distance, or angles that obscure their light. Theorists predict that many more such mergers occur across the cosmos every day. Unseen and unheard, their gravitational whispers too faint for present detectors. The silence is not absence, but limitation. A reminder that human technology has only just begun to touch the skin of a deeper reality. The horizon of discovery stretches outward, hinting that the true population of compact stars may be far greater than current observations suggest. Magnetars, too, deepen this mystery. Their outbursts are not predictable, and their fury can appear without warning. In December 2004, one such star in the constellation Sagittarius released a giant flare so intense that it briefly altered Earth's upper atmosphere. Even from a distance of 50,000 light-years, the energy released in that instant surpassed the Sun's output in 100,000 years. These events suggest that compact stars are capable of violence that borders on the incomprehensible. They are reminders that cosmic power is not evenly distributed but concentrated into rare, almost mythical sources. For scientists, these magnetar flares are both a gift and a frustration. A gift because they allow the study of matter under unimaginable conditions. A frustration because their unpredictability makes them nearly impossible to capture in detail. Each flare is a fleeting note in a symphony that human instruments are only beginning to hear. The phenomenon of rapid rotation adds yet another layer to their strangeness. Some neutron stars spin hundreds of times per second, their beams of radiation sweeping across space with clockwork precision. These millisecond pulsars are so stable that their pulses rival the best atomic clocks on Earth, and they are now used as galactic metronomes to search for gravitational waves of even lower frequency than LIGO can detect. Their steadiness suggests order, yet beneath that stability lies chaos, a mass of degenerate matter whirling at speeds that should tear lesser objects apart. The paradox is profound. Stars on the brink of destruction become the universe's most precise instruments of time. Even so, these discoveries only deepen the sense that compact stars remain perched at the extreme edge of science. They are both known and unknowable, observed yet fundamentally concealed. Every revelation leads not to closure but to further enigmas. Do they harbor exotic states of matter? Do their collisions give rise to short gamma-ray bursts, those flashes of high-energy light that blaze across galaxies? Could they be the birthplace of cosmic rays that reach energies beyond any earthly accelerator? Each question expands the horizon of mystery, pulling human thought closer to the abyss of the unknown. At their core lies a paradox. Compact stars are among the most studied objects in astrophysics, yet they resist full comprehension. They act as laboratories where gravity, quantum mechanics, and nuclear physics collide, domains that on Earth are kept apart by scale and context. In their presence, the universe forces all of physics to converge, and as long as mysteries remain unexplained bursts, hidden states of matter, missing signals in gravitational waves, they will continue to challenge science with riddles that may take centuries to unravel. The mystery of compact stars does not rest solely in their strange appearances, their pulses of light, or their rare collisions. It lies also in the unseen depths of their interiors, where matter is forced into states that stretch even the most trusted equations to their limits. Mainstream astrophysics has spent decades constructing models of these interiors, not through direct observation, for no telescope can pierce a neutron star's skin, but through the relentless marriage of theory, experiment, and indirect measurement. What emerges is a vision of matter at its most extreme, a realm where the familiar structures of atoms dissolve into something entirely alien within these collapsed suns. Protons and electrons are pressed so tightly together that they merge, leaving behind an ocean of neutrons. Yet even this description only scratches the surface. In the densest layers, neutrons themselves may flow not as a chaotic gas, but as a superfluid, a state of matter without friction, where particles move collectively as one. This superfluidity, supported by decades of nuclear theory, could explain why neutron stars rotate so steadily, why their cooling follows strange curves, and why sudden glitches, abrupt changes in rotation, ripple through their signals. Alongside this superfluid core lies superconductivity, where protons form paired states that carry currents without resistance. If these models are correct, then inside every neutron star resides not a chaotic jumble, but a perfectly ordered quantum symphony, a manifestation of the same principles seen in earthly laboratories. Magnified to cosmic proportions, the equations of state that govern such matter remain among the most difficult problems in modern physics. Laboratory accelerators can smash nuclei together, recreating densities close to those in a neutron star's crust, but never the sheer compression of its heart. Theoretical physicists must therefore weave together hints from nuclear data, astrophysical observations, and gravitational wave signatures. Whether matter stiffens or softens under pressure determines how massive a neutron star can grow before collapsing into a black hole. This balance is expressed through the Tolman-Oppenheimer-Volkoff limit, a boundary that mainstream theory places somewhere between 2 and 3 solar masses. Above this threshold, even the degeneracy pressure of neutrons cannot withstand gravity's relentless pull, and the star's fate is sealed. Below it, stability persists, and the compact core continues to exist as a neutron star, broadcasting its presence through pulses of radiation and gravitational whispers. In this way, neutron stars serve as the critical frontier between the tangible and the absolute. They define the very line at which matter yields entirely to space-time curvature, marking the transition into black holes. The mainstream view treats them not as curiosities, but as essential waypoints in stellar evolution. In their deaths, stars are not erased but recycled, their dense cores returning enriched material back to galaxies through winds, flares, and collisions. Without this cycle, heavy elements would never seed new generations of stars or planets. The death throes of massive suns, rather than an ending, become the quiet architects of cosmic continuity. Simulations now attempt to capture this cycle in ever finer detail. Computer models of stellar collapse track the moment a massive star's core implodes, following shock waves, neutrino floods, and nuclear transformations that decide whether the remnant stabilizes as a neutron star or collapses entirely into darkness. These digital reconstructions are among the most complex calculations ever attempted, consuming months of supercomputer time, yet even they cannot capture every variable. The physics of neutrino transport, magnetic turbulence, and nuclear reactions still leave gaps of uncertainty. Yet each improvement brings astrophysics closer to understanding how compact stars are born, and why nature divides their destinies with such fine margins. Through all of this, neutron stars stand as testbeds where general relativity and nuclear physics are forced into direct confrontation. Einstein's equations describe the space-time curvature that binds them, while quantum chromodynamics dictates the behavior of the matter within. Neither framework is complete on its own, but together they sketch an outline of a reality where the cosmos itself becomes a laboratory. Observing pulsar timing, gravitational wave signatures, and cooling curves allows physicists to refine these models, testing whether the mainstream theories hold. Often they do, but sometimes the data reveals subtle tensions, hints that deeper truths may be hiding within these stellar corpses. Thus, the mainstream picture is both a triumph and a doorway. It describes compact stars as dense, ordered, and predictable in their broad strokes. Neutron superfluids, superconducting interiors, defined mass limits, and roles within galactic recycling. Yet it is also incomplete, leaving gaps that the equations cannot fully resolve. Behind the stability of these models lies an unspoken awareness that even in their most accepted form, compact stars still press against the boundaries of human understanding, beckoning toward mysteries that stretch beyond what the mainstream can contain. Beneath the polished surface of mainstream theory, the layers of a neutron star reveal themselves like pages in a book written in an alien script. The outermost crust, only a kilometer thick, is believed to resemble an immense crystal lattice, nuclei arranged in an ordered pattern, immersed in a sea of degenerate electrons. This crust is not uniform. As one journeys deeper, the familiar nuclear shapes begin to distort under pressure, bending and merging into strange forms. These are the so-called nuclear pasta phases, where protons and neutrons no longer arrange themselves as spherical nuclei, but instead elongate into rods, flatten into sheets, or twist into labyrinthine structures resembling lasagna or spaghetti. Such shapes, predicted through nuclear simulations, arise because the forces that bind matter together and the crushing gravity of the star wage a delicate war, producing geometry unlike anything found on Earth. These pasta phases may be the strongest material in the universe, 1 billion times more resilient than steel, and could hold the key to understanding starquakes and magnetic outbursts that ripple across space. Deeper still, the crust gives way to the core, where neutrons dominate, but not in quiet isolation. Some theories suggest that a fraction of protons and electrons survive, forming currents that weave magnetic fields of unimaginable strength. The interaction between these protons, paired into superconducting states, and the neutron superfluid around them produces a complex dance, a quantum coupling of matter and magnetism on a stellar scale. These interactions could explain why neutron stars slow their rotation over time with such precision, and why sudden glitches occur, as if the star's interior were briefly tugged by unseen currents before snapping back into equilibrium. In the mainstream view, every irregularity observed from pulsars is a signature of this hidden quantum orchestra, playing beneath the silence of a crust thousands of trillions of tons thick. Cooling curves provide another window into this unseen world. Neutron stars are born searingly hot, their interiors reaching hundreds of billions of degrees in the seconds after collapse. Yet they cool rapidly, shedding energy through floods of neutrinos, ghostly particles that escape the star almost unhindered. The rate at which a neutron star cools depends critically on what lies in its heart. If the core is a simple neutron superfluid, the cooling follows one trajectory. If exotic states emerge, such as hyperons, meson condensates, or deconfined quarks, the cooling accelerates in ways that observations can detect. X-ray telescopes monitoring young neutron stars have already hinted at such behavior, forcing refinements in the mainstream models. Each cooling curve becomes a cryptic clue, carrying within it the possibility that ordinary neutrons are not the full story. Gravitational waves add yet another perspective. When two neutron stars spiral together and collide, the vibrations they send through spacetime encode information about their inner stiffness, their so-called equation of state. The first detection of such an event in 2017, GW 170817, provided not only a triumph for multi-messenger astronomy, but also a constraint on the size and structure of neutron stars themselves. By analyzing how the stars deformed under each other's gravity in their final orbits, astrophysicists could infer how resistant their interiors were to compression. These data ruled out the stiffest equations of state and tightened the range of possibilities for what matter at nuclear densities might be. In this way, the universe itself becomes the ultimate experimenter, tearing open neutron stars so that humanity may glimpse their secrets in the tremors that ripple through spacetime. Mainstream astrophysics continues to refine these models, weaving together crustal structure, core superfluidity, cooling behavior, and gravitational wave signals into a unified picture. Yet each refinement raises new questions. If the pasta phases are real, what precise role do they play in regulating magnetic fields and starquakes? If superconducting protons thread the core, how do they interact with the neutron vortices that anchor a star's spin? If cooling anomalies reveal exotic particles, Does this mean the interiors of neutron stars are already testing physics beyond the standard model? The mainstream approach does not dismiss such possibilities, but treats them cautiously, layering hypotheses upon observation, never straying too far from what the data allowed in the end. Neutron stars become more than stellar remnants. They stand as crossroads where nuclear physics, quantum mechanics, relativity, and astrophysical observation converge. Each pulsar timed to the millisecond, each gravitational wave ripple, each thermal spectrum recorded by orbiting telescopes is a fragment of the larger mosaic. Together, they define a mainstream view that is both precise and provisional, firm in its outlines yet unfinished in its details. It is a portrait of the cosmos at its most condensed, where the crushing force of gravity sculpts matter into new forms, and where the familiar laws of physics are pushed until they nearly break. They are called stars. But in truth they are something stranger, cosmic enigmas masquerading as the husks of suns. At the far edge of accepted science lies a realm where speculation begins to weave itself into theory, where observation brushes against the limits of comprehension. Compact stars, in their extremes, invite not only measurement but imagination. They are the laboratories where matter might reveal its most forbidden states, and where the cosmos itself hints that its laws are not final but provisional, waiting to be overturned. The idea of the quark star is one of the most provocative. In this vision, the crushing pressure inside a collapsing stellar core does not merely compress neutrons together, it dissolves them. The neutrons, each built of 3 quarks bound tightly by the strong nuclear force, break apart into their fundamental components. A sea of up and down quarks, perhaps mixed with strange quarks, could flood the star's interior. This quark matter would not resemble anything known on Earth. It would be a fluid without individual particles, a continuous ocean of the smallest building blocks of matter, flowing beneath a thin crust of neutrons. If such stars exist, they would glow differently, cool differently, and carry rotational signatures unlike ordinary neutron stars. Some candidates have already been whispered about in astronomical data. Stars too small or too dense to fit within standard models, as though hiding a more exotic heart. From this arises the even bolder hypothesis of strange matter, a form so stable that once created, it could consume all other matter it touches. Strange quarks, when blended with up and down quarks, might form clusters more tightly bound than atomic nuclei. If true, a fragment of strange matter, a strange late, could transform ordinary neutrons into more strange matter, upon contact, spreading like an infection. This unsettling possibility raises the question: if strange matter is stable, could entire stars be made of it, their interiors alien oceans of quark-gluon plasma? Some theorists have suggested that strange stars might explain anomalous bursts of energy seen from deep space. But for now, the idea remains suspended between fear and fascination. Speculation does not end at quarks. Some models propose hybrid stars, celestial structures layered like onions. Their outer shells would mirror the neutron stars we know, but buried beneath would lie an exotic inner core of deconfined quarks, or even more bizarre phases, hyper-unrich matter, kaon condensates, or color superconductors where quarks pair in quantum states spanning the whole star. Each layer would alter the star's observable properties, shaping how it spins, how it radiates, and how it dies, observationally distinguishing such hybrids from ordinary. Neutron stars remains one of the frontier challenges of modern astrophysics. Every irregular pulse, every gravitational ripple, might be a clue. Others take the speculation further, asking whether compact stars are not simply dense objects, but cosmic gateways. Some theories of quantum gravity hint that, under extreme densities, spacetime itself might fracture, allowing compact stars to act as windows to hidden dimensions. If extraspatial dimensions exist, as some string theories propose, then perhaps the cores of these stars touch upon them, bleeding gravitational energy into unseen realms. A neutron star that cools faster than predicted, or spins down in ways unaccounted for, could be whispering of physics beyond 4 dimensions. Relativity itself trembles at these frontiers. Einstein's theory predicts the thresholds between stars, neutron stars, and black holes with astonishing success. But quantum mechanics insists that infinities and singularities cannot be the whole story. Some speculative cosmologies propose that compact stars, under certain conditions, may collapse into objects that are not black holes at all, but something stranger gravastars, dark energy-supported shells, or even seeds of new universes budding off from our own. If true, every compact star on the verge of collapse would be a cosmic gamble, deciding not only its fate, but perhaps the fate of universes unborn, in this shadowed territory between science and imagination. Compact stars become mirrors of human curiosity. They remind us that physics is not finished, that what we call mainstream may someday be the mythology of a simpler age. They are not just remnants of stellar death, but perhaps harbingers of new laws, new states of matter, and new realities. The stars may be silent, but within their silence lingers the possibility that the universe is far stranger than anyone dares to believe, at the outer rim of imagination, where theory blurs into myth yet remains tethered to mathematics. Compact stars stand as riddles daring science to answer. For decades, astrophysicists have tested equations against observation, but there remain gaps, silences that resist explanation. In those gaps, speculative models take root. Each offers a different vision of what lies beneath the crust of a collapsed star, and each forces a confrontation with the limits of human understanding. The quark star hypothesis is perhaps the most disciplined of these ventures, resting on the foundation of particle physics itself. Neutrons, once thought indivisible, are known to be made of quarks bound by gluons in a storm of quantum color charge, when a collapsing core crushes matter beyond nuclear density. The pressure may become so immense that neutrons disintegrate into their constituent quarks. A new equilibrium could arise, not as separate particles, but as a quark-gluon plasma, a liquid sea where distinctions between individual building blocks vanish. Laboratory accelerators, like the Large Hadron Collider, create fleeting droplets of this state for microseconds. Yet inside a compact star, the same matter might persist for billions of years, sculpting a star whose properties could betray its existence, smaller than neutron stars, but heavier and perhaps radiating with a cooling pattern that does not match theory. A handful of observed stars, defying neutron star equations of state, remain unresolved ghostly candidates, neither fully confirmed nor dismissed, lingering as possible quark stars. Stranger still is the notion of strange matter. This concept proposes that matter infused with strange quarks might be more stable than any form we know. If so, a fragment of strange matter could transform normal nuclei into strange ones, catalyzing a runaway reaction that could spread across an entire star and, in principle, to any matter it touched. Though the nightmare vision of a strangelet devouring the Earth has been dismissed as unlikely, the broader idea remains scientifically alive. If strange stars exist, their magnetic fields, thermal emissions, and oscillations might differ in subtle ways from their neutron star cousins. Detecting such signatures requires precision astronomy beyond what current telescopes can reliably offer. Yet in the faint irregularities of pulsar timing, some researchers suspect faint echoes of a strange interior dot beyond the boundaries of nuclear physics. Other speculative visions emerge. Hybrid stars represent a compromise between the conventional and the exotic, an outer mantle of neutron matter surrounding an inner core of quark plasma or hyperonic matter. These layered interiors could explain why some pulsars achieve extreme rotational speeds without tearing themselves apart, or why others resist collapse despite approaching the Talman-Oppenheimer-Volkoff mass limit. In computer simulations, hybrid stars display unique oscillation modes, potential fingerprints detectable in gravitational waves. Each ripple in spacetime captured by LIGO or Virgo may hold within it the hidden architecture of such a star, encoded like a secret waiting to be read. More radical still are proposals that compact stars might not be endpoints at all, but thresholds. Certain models of quantum gravity suggest that when matter is pressed beyond neutron densities, spacetime itself may alter. Instead of collapsing into singularities, stars could stabilize into exotic configurations. Gravastars, hypothetical objects where a thin shell of matter traps a core of dark energy. Or boson stars, composed not of fermions like neutrons, but of scalar particles yet undiscovered. These models, though speculative, attempt to resolve the paradox of singularities that relativity cannot explain and quantum mechanics cannot tolerate. If such stars exist, they could mimic black holes in many ways, yet differ in telltale signal subtle variations in gravitational waveforms or electromagnetic emissions. Even wilder ideas drift through the literature. Some physicists have wondered whether compact stars, in their collapse, might tunnel through to other dimensions predicted by string theory. In this view, the death of a massive star might birth more than a remnant. It could seed a pocket universe, invisible to us except for the gravitational scars left behind. If true, every black hole candidate might conceal not an abyss but a bridge. Every compact star a potential experiment in. These ideas remain untestable, yet they persist because compact stars push every known theory to its breaking point. They force physics to imagine what lies beyond its own horizon. Such speculation is not idle fantasy, but a necessary act of science at the edge of the unknown. History shows that what begins as speculation often becomes the foundation of new understanding. Pulsars were once dismissed as impossible. Black holes were ridiculed as mere artifacts of mathematics. Today both are observed realities, woven into the fabric of astrophysics. Quark stars, strange matter, hybrid interiors, even exotic gateways, any of these could, in time, move from fringe to fact. Until then, compact stars continue to flicker as beacons not only of collapsed matter, but of unfinished knowledge. They remind humanity that even in the age of precision telescopes and gravitational observatories, the universe retains its secrets, waiting for instruments yet unbuilt, for theories yet unspoken, and for minds willing to cross the boundary between what is known and what is still feared to be impossible, high above Earth. A quiet constellation of machines listens to the heartbeat of the cosmos. They are not the gleaming observatories of glass lenses once raised by stargazers, but a web of radio dishes, orbiting telescopes, and detectors of invisible ripples in spacetime. Together they form a vast network, stretching across continents and skies, united by a singular pursuit, to chart the lives of the densest stars in existence. Pulsars, those spinning beacons of collapsed suns, are tracked with a precision so great that a single tick of their rotation rivals the stability of the most advanced atomic clocks. These cosmic lighthouses sweep their beams across the galaxy, and in their rhythms, scientists search for subtle shift signs of unseen companions, whispers of gravitational waves, or the faint drag of exotic physics at work within their cores, in low Earth orbit. The NASA instrument aboard the International Space Station turns its gaze upon neutron stars. With its X-ray eyes, it measures the heat of their surfaces, the way their light bends as it escapes immense gravity, and the silhouettes they cast upon the fabric of spacetime itself. From these observations emerges a map, not of geography but of possibility, the neutron star equation of state, a mathematical attempt to describe how matter behaves when crushed beyond atomic boundaries. Each data point sharpens or erases entire classes of theory, ruling out some exotic models while leaving others standing as fragile candidates for truth. Yet the riddle remains unfinished, for even the best measurements suggest answers balanced on the edge of uncertainty. On Earth, experiments echo this celestial pursuit. In underground laboratories and particle accelerators, physicists collide heavy nuclei to recreate, for fractions of a second, the pressures found in stellar cores. Detectors record the showers of fragments, measuring how nuclear matter compresses, flows, and breaks apart. These collisions, violent yet controlled, are the closest humanity can come to conjuring the physics of a dying star. The results feed into supercomputers, where simulations of neutron star interiors attempt to reconcile theory with observation. Billions of variables are woven into digital stars, their cores compressed until quarks, hyperons, or other exotic forms of matter emerge on screen as mathematical ghosts. The models spin, merge, collapse, and cool in silico, mirroring the same violent ballet that telescopes record across the universe. The work is not only technical but philosophical. Each new equation, each observation, forces a confrontation with nature's capacity to surprise. Theorists must walk a narrow line between mathematics elegant enough to describe reality and humble enough to admit its own incompleteness. Astrophysicists confront an unsettling truth. The more closely compact stars are studied, the more alien they appear. The surface measurements suggest oceans of superfluids and superconductors, where quantum laws rule entire worlds. Gravitational waves hint at tidal forces so intense that space-time itself becomes an elastic medium, stretching and rebounding as stars collide. Yet the interiors remain hidden, shielded by matter so opaque that no light escapes to betray its true form. Still, confidence grows that the coming decades will not merely refine knowledge but transform it. The next generation of gravitational observatories, more sensitive by orders of magnitude, will capture the full symphony of neutron star collisions. Radio arrays stretching across continents will detect nanohertz gravitational waves, tracing the influence of compact stars on galactic scales. Future X-ray telescopes will measure their mass and radius with clarity that dissolves today's uncertainties. And as experiments in nuclear physics press further into extremes of density and temperature, the laboratory may one day confirm what the stars have hidden for eons. Yet even in this anticipation, a shadow lingers. Each answer risks unveiling deeper mysteries, whether quarks truly roam free in stellar cores, whether new states of matter exist, or whether compact stars hide windows into new dimensions of physics itself. the scientific effort continues not only as a quest for knowledge, but as a dialogue with the unknown, an acknowledgement that the universe guards its secrets fiercely. Compact stars, so small and yet so immeasurably powerful, remain as both laboratories and enigmas. They are reminders that the frontier of science does not lie only in distant galaxies or in the mathematics of the very small, but also in the haunting silence of collapsed suns, where human understanding bends, fractures, and waits to be remade. In recent years, NASA has already begun to whisper answers to questions that once seemed unreachable. Its careful measurements of pulsars, like J0030 plus 0451, have revealed their dimensions with unprecedented accuracy, mapping how light bends around their crushed forms. These results narrowed the possible equations of state, showing that neutron stars are not infinitely rigid spheres, nor are they as soft as some exotic models had once suggested. Instead, they occupy a fragile balance rigid enough to withstand collapse, yet supple enough to compress matter into new arrangements of particles. Each dataset draws the circle tighter, leaving less room for speculation and forcing theory to converge with reality. Yet, as often happens in science, the clarity is double-edged by ruling out the impossible. The observations sharpen the strangeness of what remains beyond Earth's orbit. Future plans gather momentum. The square-kilometer array, a colossal network of radio antennas stretching across the deserts of Australia and South Africa, promises to transform pulsar astronomy. With it, astronomers will monitor thousands of pulsars simultaneously, creating a galactic-scale observatory of time itself. Their regular pulses, spread across light years, will be woven into a tapestry so precise that even the faint tug of gravitational waves rippling from the dance of supermassive black holes will be recorded. Within that tapestry may lie signatures of neutron star behavior, yet unseen glitches in their rotation, subtle distortions caused by their interiors rearranging under pressure, or unexpected shifts hinting at the presence of quark matter beneath their crusts. Meanwhile, supercomputers continue to grow into artificial laboratories where theory collides with reality. In their simulated universes, entire stars are born, burn, collapse, and collide within hours of computation. Codes once limited by memory and processing now weave in nuclear physics, general relativity, and magnetohydrodynamics into unified portraits of stellar death. These digital stars collapse with eerie fidelity, producing gravitational waves that can be compared directly to LIGO's observations. Every mismatch between model and data signals a missing ingredient in human understanding, perhaps a new force, an overlooked particle, or a property of matter that only emerges under crushing densities. The gap between simulation and sky becomes less a failure than a beacon, pointing toward realms of physics still unrevealed. On Earth, heavy-ion collisions at particle accelerators such as RIC and the Large Hadron Collider bring humanity closer to tasting the stuff of neutron star interiors. By slamming gold nuclei together at near-light speeds, scientists recreate fleeting moments when quarks and gluons swim free in a quark-gluon plasma. For microseconds, the laboratory echoes conditions that may exist in the hearts of compact stars. Detectors capture showers of particles and energies, data points that feed directly into the astrophysical quest. Though the scales are different microscopic collisions versus macroscopic stars, the underlying physics is shared. Like two verses of the same cosmic song, the work is slow, methodical, yet infused with awe. Each observatory, each experiment, is a fragment of a larger vision, to see not only the stars themselves, but the laws of nature written within them. The boundaries between astronomy, nuclear physics, and relativity blur, replaced by a shared frontier where every discipline contributes to understanding. Astronomers become custodians of time, physicists custodians of matter, and computer scientists custodians of possibility. Together, they form a community united by the recognition that compact stars are not curiosities but crucibles of truth. Their silence heavier than words, their light sharper than equations, and still patience is demanded. The universe reveals itself reluctantly, granting answers in fragments, never all at once. Observations arrive, clouded with uncertainty. Simulations strain against unknowns, and experiments wrestle with the limits of technology. Yet within this tension lies the very heart of discovery, the awareness that compact stars are not simply astronomical objects, but challenges posed by the cosmos itself, puzzles designed to stretch the reach of human thought. In their crushing density, they hold not only matter but meaning, not only gravity but the gravity of knowledge itself. They endure in silence. The compact stars, neutron stars, pulsars, magnetars, hearts of collapsed suns that still beat across the void. Once radiant spheres of fusion, they have shed their brilliance. Yet in their demise, they have become something stranger, more enduring. Each turn of their magnetic fields, each steady pulse of radiation, is like the ghostly rhythm of a cosmic heart still echoing long after death. They are not merely remnants. They are reminders that even in collapse, the universe finds a way to keep beating. To gaze upon them is to measure human smallness against immensities beyond comprehension. A teaspoon of their matter outweighs mountains. Their gravity warps time itself. Their densities defy the imagination. Around them, light bends, space trembles, and the equations of physics grow uncertain. What the mind struggles to grasp, the heart feels instinctively. A humility before forces that reduce every triumph of civilization into whispers beneath eternity. Yet within that humility lies not despair, but perspective. For if the universe can compress entire suns into fragments smaller than cities, then the fragility of human life becomes not meaningless, but precious. In these compact hearts, destruction is never final. The collapse of a star scatters its ashes into space, forging iron, gold, and the calcium in every bone. The death of the old births the possibility of the new. Galaxies are seeded by the ruins of stars, and planets form from the dust of their corpses. Even neutron stars themselves, when they collide, release torrents of heavy elements, filling the cosmos with the ingredients for life. It is a paradox written in starlight. Every ending is a beginning in disguise. Perhaps this is their greatest lesson, that resilience is not about resisting collapse, but about transformation through it. Suns die, yet their cores endure. Worlds perish, yet their elements return to weave new forms. In the unthinkable pressures of compact stars lies a reflection of endurance, an unyielding truth that the universe survives by remaking itself, and so a final question lingers in their silence. One that humankind can neither ignore nor yet fully answer. When the universe twists its own fabric under the crushing force of compact stars, are we witnessing the first cracks of its death or the promise of an eternal rebirth? They sit in the silence of the cosmos, immovable witnesses to the passage of billions of years, carrying within them the memory of a violent birth. Compact stars are not only the fossilized remains of stellar lives, they are living paradoxes. Compressed to the brink of matter's endurance, they become more than the sum of their collapse. Their magnetic fields crackle like invisible storms. Their rotations mark the passage of cosmic seconds with unerring precision. Their surfaces bear stresses that would tear apart any known material. They embody the strange lesson that only through destruction can something so profoundly new emerge. The quiet rhythm of their existence whispers of endurance, a static endurance, but one carved from change, from death itself made into persistence. Every observation of these dense hearts of matter turns into a mirror held back toward humanity. What does it mean that the same universe that forges such titanic forces also created minds fragile enough to ponder them? A civilization bound to a thin biosphere on one small world can, with mathematics and light, reach across time and space to decode the tremors of neutron stars colliding 100 million light-years away. Against the backdrop of forces that warp spacetime, the human endeavor may seem small. Yet its very smallness carries a profound weight, frailty daring to contemplate eternity. It is as if compact stars remind us that existence itself is not about dominance over scale, but about the courage to stand before immensity and still seek meaning within. Their silence lies the story of cycles without end. Stars collapse, but in their collapse they release the seeds of life. Heavy elements fall like ashes across the galaxy, to be gathered into new stars, new worlds, new beings that one day will wonder at the process itself. If compact stars are cosmic hearts, then their pulse is not only the beat of their own survival, but the rhythm of continuity across time. From them comes a lesson both sobering and comforting. Nothing is ever truly lost. Matter, energy, and even the patterns of existence find ways to return, to reconfigure, to echo in forms yet unseen. In this way, compact stars are not only laboratories for physics, they are symbols of resilience. They show that the deepest transformations emerge only under pressure. That collapse can conceal within it the possibility of rebirth. They do not resist gravity's pull, but surrender to it, and in surrendering, they achieve a new kind of permanence. Their story reminds humankind that even fragility, even endings, may be gateways to endurance in another form. Thus, they pose one final, lingering question, both scientific and spiritual. When the universe bends under its own crushing weight, when time and matter are compressed into near invisibility, are we seeing the last tremors of a cosmos on its way to silence? Or the gestation of something beyond imagining, in the glow of compact stars? The answer remains suspended, waiting in the stillness, like the faint heartbeat of creation itself. They rest in the vast night, suspended like embers of forgotten fires. Compact stars that once blazed as suns, but now exist as shadows of their former selves. Yet in their silence they speak louder than any living star. They whisper truths about endings and transformations, about the strange bargain the universe has struck between destruction and creation. They are monuments of collapse, frozen at the brink of infinity, where gravity bends time itself and where matter is crushed into forms that seem impossible to endure. These remnant scores so dense they could fit mountains into the space of a pebble, challenge imagination and redefine what permanence means. They are not corpses, though they were born in death. They are not beginnings, though they seed beginnings in their wake. They exist as cosmic hearts, dense and unyielding, still beating their slow, unearthly rhythms into the silence of space. The human gaze toward them is not only a search for knowledge, but also a search for perspective. For when eyes and instruments look into the void and find pulsars blinking with the steadiness of clocks, or magnetars erupting with bursts that could erase the atmosphere of a planet, something more than science stirs. There arises a sense of proportion, a recognition of scale, a humility that softens the borders of ego. What does it mean that the universe, in all its indifference, carries within its structures so violent, so absolute, and yet so beautiful? What does it say about existence itself, that from fire and collapse come elements that become oceans, soil, blood, and breath? In compact stars, the distance between human frailty and cosmic immensity narrows, for both are bound to the same cycles of transformation. To stand before the knowledge of such stars is to confront a paradox. On one hand, they reveal human smallness, civilizations fleeting, histories vanishing in the time it takes a pulsar to spin once. Yet on the other hand, they reveal human significance, for only through consciousness does the universe become aware of itself. Matter that once dwelt in stars has become eyes that look back at the stars, minds that calculate the crushing densities of neutron matter, hands that build machines to catch the ripples of spacetime itself. If the universe writes its story in the collapse of stars, then humanity is the pen that first makes the story legible. Without witnesses, even the most violent events would pass unmarked. With witnesses, they become history, myth, reflection. The lessons compact stars offer are profound because they reach across the border between physics and philosophy. They remind us that survival is not always about resisting pressure, but about transformation under it. They show that finality is rarely absolute, for endings dissolve into beginnings, and what appears as death in one frame of time becomes the seed of renewal in another. Supernova shatter, and from their dust come worlds. Neutron stars remain impossibly compressed, and from their presence come lessons that stretch human knowledge toward its breaking point. These objects embody resilience, not by avoiding collapse, but by enduring through it, by making catastrophe something stable, something enduring, something new. There is also a darker reflection. In their silence lies the reminder that the universe is not built for human comfort. Gravity does not bend for human longing. Magnetic storms do not pause for human survival. Compact stars reveal the sheer indifference of nature. Their forces would tear apart molecules, strip atmospheres, reduce planets to debris. They show that the cosmos is not safe, not gentle, not made in human image. And yet, within that indifference lies a deeper beauty. The same forces that obliterate also forge. The same collapse that consumes a star releases the gold in a wedding ring, the iodine in a human body, the platinum in a satellite's circuitry. In the indifference of compact stars lies the strange generosity of existence, where creation and destruction are bound together so tightly they cannot be separated. This paradox extends beyond science into the human condition. For in every life there are pressures that threaten collapse, forces that bend the fabric of existence. People too are compacted by grief, by loss, by change that cannot be resisted. Yet like stars, such collapse may not be the end. From it can emerge resilience, transformation, new forms of strength. The metaphor is not forced. It is written into the very matter of human bodies. Every atom of iron in human blood was forged in a star that collapsed long ago. Humanity is not only like the stars, it is literally made of them. Compact stars, then, are more than objects of study. They are kin, distant relatives in the great family of matter, older and harder, but bound by the same cosmic ancestry. Time, too, takes on new meaning when measured against compact stars. A pulsar spins hundreds of times per second, marking time with a precision no human clock can rival. Yet even as they tick so fast, they endure for millions of years, their rotation slowing only imperceptibly with age. Magnetars erupt in seconds, but the scars of their storms linger across eons. 4 black holes born from collapse. Time itself bends, and what is outside may never match what is inside. Humanity, caught in its brief span of decades and centuries, finds in these objects both a reminder of mortality and a vision of eternity. The pulse of a neutron star is not a rhythm anyone can hear, yet it beats like a drum across the void, whispering of the patience of the cosmos. Philosophers once asked whether the universe had meaning. Compact stars suggest that meaning is not given, but made. They offer no answers, no comfort, no intention, and yet, in their silence, they create the possibility of meaning, for by observing them, by learning from them, by seeing the cycles they embody, humanity finds reflections of itself. The meaning lies not in the stars, but in the gaze that seeks them. When humans call them cosmic hearts, it is not because the stars themselves feel, but because humanity projects its own questions onto them. What endures? What transforms? What survives collapse? Their extremes also gesture toward mysteries still unsolved. Do neutron stars hide quark matter in their cores? Do magnetars conceal physics beyond the known laws? Does the boundary between neutron star and black hole mark not an end, but a doorway to something else? The pursuit of such questions is not only scientific but existential, for each discovery reshapes humanity's place in the cosmos. To find strange matter would mean the universe harbors states of being beyond anything terrestrial. To glimpse the edge of relativity's power would mean that even Einstein's vision is not final. To see compact stars as seeds of universes would mean existence itself is recursive, repeating endlessly through collapse and rebirth. In this light, compact stars become more than objects. They are thresholds. They mark the borders of knowledge, where human understanding falters but curiosity presses forward. Each gravitational wave detected, each burst of gamma radiation recorded, each pulsar's rhythm mapped is a step toward the unknown. Compact stars do not yield their truths easily, but in withholding they invite pursuit. They remind humanity that mystery is not a barrier but a horizon, that the unknown is not emptiness but potential. In the crushing weight of their gravity lies the weight of unanswered questions, waiting to be drawn out across time. Their silence becomes almost sacred, not sacred in a religious sense, but in the sense of awe, reverence, and humility they inspire. To know they exist, to trace their light across millions of years, to measure their pulse against the vastness of time, is to step outside the narrow bounds of daily life. It is to feel, if only for a moment, the immensity of which humanity is a part. Compact stars are reminders that the universe is not just background to human stories, but the stage upon which all stories unfold, and beyond which lies the unending dark. And so the reflections return to a single question, one that lingers like a heartbeat at the end of a vast symphony. When the universe twists its own fabric under the crushing force of compact stars, is it showing the last echoes of its life, or the first whispers of its rebirth? The answer may never be given, but perhaps the answer is not the point. Perhaps the point is the act of asking, the courage of wonder, the recognition that even in the face of forces that bend light and time, humanity still seeks meaning. That search itself becomes a kind of endurance, a reflection of the same resilience compact stars embody. For as long as compact stars endure, The universe holds a mirror. In their crushing silence, humanity sees both its fragility and its strength, its brevity and its continuity, its smallness and its capacity to reach across galaxies with thought. They are cosmic hearts, yes, but they are also cosmic teachers. And their lesson, whispered through the silence of the void, is that collapse is not the end. It is the beginning of something deeper, something stranger, something yet to be born.